Assalamu alaikum. In this lecture, I will talk about standing waves on a string of fixed length. This is the string of length L. It's fixed at x equals 0 and at x equal L. The impedance here is infinity and at the other end is infinity. We know that the solution of the wave equation is given by this form. The first term is the incident wave and the second term is the reflected wave. When the wave reached the second end, it reflected out of phase because Z2 greater than Z1. Now we have to satisfy the boundary condition for this equation. That's y equals 0 at x equal n and y equals 0 at x equal l. Now the first condition gives that b equal minus a. In this case, the wave has this shape. Now this satisfies the wave equation. We need to substitute d2y by dt squared to get rid of the time dependent. We get this for d2y by dt squared, which is minus omega square y. Substitute here. We get this equation that depends on x only. The solution for this, we know it's sine k L. Now, for this solution, to satisfy x at equal L, that sine KL must be 0. In this case, K sub NL is a multiple of y, where n is 1, 2, 3, etc., an integer. So the frequency of the nth mode is n by V over L. This is in terms of V, this is in terms of the natural frequency. Now, if we look at this, we find that L must be half integer of lambda. That is, the length of the string must be lambda over 2 for n equal 1, lambda for n equal 2, 3 halves lambda for n equal 3. Note for n greater than 1, 2, 3, there are positions along the string which are always at rest. This is here, L over 2 is at rest. This position is at rest. We call it node, actually, at node point, and this is at rest. Now that the energy, if we look at this, if we estimate the incident energy and the reflected energy, the net energy is 0. That's why we call it, or the flux of energy is 0 in this case. That's why we call it standing waves. Therefore, standing waves arise when a single mode is excited and the incident and reflected wave are superposed. Usually the reflection is not complete, then we speak of a standing wave ratio. Now let's find the displacement of the nth mode. That's we have to replace in this y omega by omega n and k by k sub n, and then simplifying we get this form with the amplitude as a square root of an square plus bn square. Now let's talk about the energy in each mode, each normal mode of a vibrating string. That's E sub k or E sub n. This is the kinetic energy. We need this for the nth mode. We have to estimate the potential energy for the nth mode. Kinetic energy is half rho dxy dot square. Y dot square is the square of the velocity of the wave. Rho dx is dm. Now the potential energy is the work done by the tension extending dx into d sub s when the string is vibrating. ds is the arc length, which is given by this equation. So the potential energy is the integration of ds minus dx. Now to evaluate this integration, we have to expand this in terms of polynomial equations as 1 plus x to the power n equal 1 plus nx, where x now is dy by dx and n is half. Doing so, one cancels with the other one, and then the n is half, so it's half times t is constant, times dy by dx, the whole thing square dx. Now we have to replace y by y sub n, y dot by y dot n, and dy by dx by dy sub n by dx. For the nth mode, this is the kinetic term, and this is the potential term. Y sub n is given by this. For this term to evaluate, we need dy sub n by dt, and for this we need dy sub n by dx. Doing so, we get this form for the kinetic energy, and this is for the potential energy. We have to integrate sine square here. You have to convert it into 1 minus cosine 2 theta over 2, and for cosine square you have to convert it into 1 plus cosine 2 theta over 2. Then adding, after performing the integration or calculating the integration, adding the kinetic term plus the potential term, we get the total energy, which is given by this expression. Here, a note that the total displacement is the summation over n of y sub n. And to give a complete solution for this problem, we still need what's called the initial condition, and it is a subject in chapter 10. Now let's talk about wave groups and the group velocity. We did this in the class at the beginning of this semester. Here we have two waves of same amplitude, y1 equal a cosine omega t minus k1x, and y2 equal a cosine omega 2 minus k2x. I will assume that omega 2 minus omega 1h is a small quantity. So adding this, we get this expression. This is the superposition. Now we have an envelope that have this speed, a slowly varying function, or with this speed omega 1 minus omega 2 over 2, and we have the vibrating the vibrating wave, which has a higher speed omega 1 plus omega 2 over 2. Remember that omega 1 minus omega 2 is a small quantity. Now we define the group velocity as delta omega over delta k, or omega 1 minus omega 2 over k1 minus k2, in if a special case of omega 1 over k1 equal omega 2 over k2. In this case, the phase velocity is the same as the group velocity. Now this is the what we are looking for is delta omega by delta k, which is the group velocity. Take the limit as delta approaches 0, then we left with d omega by dk is v group. Now substitute for omega by kv, we get this expression. V group is v plus k dv by dk. Now we have three cases when v equal v a group. This is called non-dispersive medium. If v group lesser than v, it's called a normal dispersion. This happens in dielectric materials. And when v group, the third curve, when v group is greater than v, the third curve, this is called anomalous dispersion. This happens in conductors. That's it. Thank you.